In this example, you are given the differential equation dy by dx equals sine x plus y minus e to the x. The initial condition, y of 0 equals 4, and a step size of h equals 0.1. Using this information, you will find the coordinates of 5 points that lie on the graph of the approximate solution to this differential equation. Substituting the initial condition, 0, 4, into the differential equation, you obtain dy by dx equals sine 0 plus 4 minus e to the 0 equals negative 1.7568 ... You see this result in the table, the first row and last column. You will use the recurrence formulas to find the coordinates of the other points. xn plus 1 equals xn plus h. yn plus 1 equals yn plus h multiplied by f of xn yn. Notice that the fourth column in the table is dy by dx evaluated at the point xn yn, which is needed to evaluate the y-coordinate using the recurrence formula. Using x0 equals 0 and y0 equals 4, substitute these into the recurrence formulas to find x1 and y1. x1 equals 0 plus 0.1 equals 0.1, and y1 equals 4 plus 0.1 multiplied by negative 1.7568 ... equals 3.8243 ... You see this result in the second line of the table. Notice that the value in the fourth column, dy by dx at xn yn, you need then in the subsequent line to evaluate yn plus 1. You now have the point 0.1, 3.8243 ... in addition to the initial value 0, 4. You can already see that the distance between these 2 points is indeed very small. Continuing in this way to find the next point, x2, y2, x2 equals 0.1 plus 0.1 equals 0.2, and y2 equals 3.8242 plus 0.1 multiplied by negative 1.8104 equals 3.6432 ... Notice that in the previous line, dy by dx is negative 1.8103 ... and in this calculation we use negative 1.8104. This is because the infinite decimal in dy dx is rounded to 4 decimal places for the calculation of y2. Continue to use the recurrence formulas to find the rest of the points. You will then graph the points xn, yn for n equals 0 to n equals 5 and join them with a smooth curve. In Part B, you will use the graph to find an approximate solution to the differential equation when x is 0.5. To do this, go to x equals 0.5 on your graph and read up to its corresponding y value, which you can see is approximately 3.1, or to be more precise, 3.06. Since you are only approximating the solution, it is all right to give your answer to 1 or at most 2 decimal places. Would it have been possible to solve the differential equation at a particular x value using any of the analytical methods you have seen in this chapter? Indeed, it is not possible to rearrange the differential equation to suit any of the forms necessary for an analytical solution. Therefore, only an approximate solution is possible by using Euler's method.